In this video, I'd like to talk about the gas laws, as described in Chapter 11.2. Let's begin by considering a sample of gas trapped inside a container. And here are the particles that make up the sample of gas. The question is, what properties of this sample of gas can we actually measure? What properties can we put a number on and record? Well, if you think about it, you'll realize there are several. One, we can measure the volume occupied by the sample of gas. If we place a pressure gauge on the container, we can measure the pressure that the gas exerts. With a suitable device, we can measure the number of particles in the sample of gas, which I'll symbolize with lowercase n. And if I have a thermometer or some other device, I can measure the temperature of the sample of gas. So, there are four measurable properties we're going to deal with. The pressure exerted by the sample of gas, which we will commonly measure in atmospheres. The volume occupied by the sample of gas, for which we'll mostly use liters. The number of particles in the sample of gas measured in moles, and the temperature of the gas in Kelvin. So the question is, how are these properties related to each other? The answer to the question is the gas laws. The gas laws are simple mathematical relationships, that is, equations, among these four properties. So, what we are going to do is the following. Use the gas laws to solve quantitative problems that relate these variables to each other, and explain the gas laws in terms of the kinetic molecular theory, which we talked about earlier in this unit. So let's begin. How are pressure and volume related to each other? Well, let's do an experiment in which we take a sample of gas in a cylinder with a movable piston on the left. The piston can move up and down. A certain pressure P1 is exerted on the sample of gas and it occupies a certain volume V1. What happens to the volume as we increase the pressure at constant temperature? Well, as you would predict and as you saw in class, as the pressure increases, the volume decreases. Why would that be? How can we explain in terms of the kinetic molecular theory why as the pressure increases, the volume decreases? Well, we talked about this before. Gases are compressible because, according to the kinetic molecular theory, the gas particles are very, very far apart from each other relative to their size, so the volume of the particles is essentially zero. Or in other words, there is so much space between the particles, it's not that hard to get them a little closer together. So, how are pressure and volume related to each other? Well, we learned early in the course that if as one variable increases, the other decreases, these two variables are inversely proportional to one another. This quantitative relationship was first discovered by the Irish scientist Robert Boyle in 1662. What is that, 360 years ago almost? Who says, according to Boyle's law, the pressure and volume of a sample of gas are inversely proportional to one another at constant temperature. What does that look like mathematically? Well, you recall that if two variables are inversely proportional to one another, that means that as one increases, the other decreases, or they multiply together to give a constant. So Boyle's law can be written either as the product of the pressure and volume is a constant, or dividing both sides by pressure, the volume is equal to that constant times the reciprocal of pressure. Lowercase k represents a constant, which in this case depends upon the temperature and the number of moles of gas. What does that look like graphically? Well, you also recall from earlier in the year that if two variables are inversely proportional to each other, then as the pressure increases, the volume decreases, and the graph looks something like this. But if I'm graphing volume as a function of reciprocal pressure, volume being the dependent variable and reciprocal of pressure being the independent variable, then as 1 over pressure increases, the volume would increase as well. So volume is directly proportional to reciprocal pressure. Both of these are ways of representing Boyle's law mathematically and graphically. Now, let's consider a situation where we have a sample of gas under some initial conditions where P1 is the initial pressure and V1 is the initial volume. If we change either the pressure or the volume, the other one changes too, and now we have a new pressure and a new volume, which I'll call P2 and V2. Now, as long as temperature and moles are constant, the constant K is the same for both, so if they're both equal to K, they must be equal to each other, and I have now what's called Boyle's law for changing conditions, P1 V1 equals P2 V2, or the product of the initial pressure and initial volume, is equal to the product of the final pressure and the final volume. And you can already predict the types of problems we're going to see. In an equation that has 4 variables, you'll be given values of 3, and you simply need to rearrange and solve for the 4th. So let's do an example of that. A sample of krypton gas at an initial pressure of 1.26 atmospheres occupies a volume of 7.40 liters. To what volume must the gas be compressed so it exerts a pressure of 3.18 atmospheres? Let's think about the steps to follow. Step number 1, write the equation that describes the problem. Step number 2, if you want to, and it's helpful, you can list the variables. What are the values of the variables you have? Number 3, rearrange your equation algebraically to isolate the variable you're solving for. Then plug in your variables with units, of course. Always have to include units in your work. Calculate, put units on your final answer, round to the correct number of sig figs, put a box around it, and then check your work. Is it reasonable? So let's attack this problem using the following steps. So we see that the problem involves pressure and volume, so we know it's going to be a Boyle's law problem. So we will begin by writing down the equation. P1V1 equals P2V2. What do we have? Well, let's go back and list our variables. So our initial pressure is 1.26 atmospheres. Our initial volume is 7.40 liters. The question asks, to what volume must the gas be compressed? That means we're looking for V2. So that it exerts a pressure of 3.1 atmospheres, that must be our final pressure, P2. Okay? So now I'm going to rearrange algebraically to isolate the variable I'm trying to solve for, which is V2. To get V2 by itself, we'll divide both sides by P2. P2 cancels, and I have my rearranged equation, which is V2 equals P1 V1 over P2. You don't need to show the algebra, but you do need to show the rearranged equation that you're plugging into. Now I can plug in my values. Let's go back up and look at those again. P1, my initial pressure, is 1.26 atmospheres. V1, my initial volume, is 7.40 liters. P2, my final pressure, is 3.18 atmospheres. Let's check and see what units cancel. I've got atmospheres in the numerator canceling atmospheres in the denominator. Looks good. I perform the calculation on my calculator, and I see the final volume I'm looking for is 2.93. I round that to 3 significant figures because each of my initial measurements had 3 significant figures. The unit I'm left with is liters, and I will draw a box around my final answer. Okay? Is that reasonable? Yes, I more than doubled the pressure. So we would predict that the volume would decrease by more than a factor of 2. 2.93 liters, 3 liters is less than half of 7.40 liters, so it makes sense. Let's move on. Next question, how are volume and temperature related to each other? Well, let's do an experiment in which we have a gas in a cylinder with a movable piston. This is on the left, and we're going to let the piston move up and down freely because the pressure is constant. It occupies a certain volume, V1, at a certain temperature, T1. If we increase the temperature at constant pressure, what's going to happen to the volume? Well, as you would predict and as you will see, as the temperature increases, the volume increases as well. Why would that be? How would the kinetic molecular theory of gases explain why the volume occupied by the sample of gas increases as the temperature increases? Well, let's go back and think about what the kinetic molecular theory actually says. As the temperature of the gas increases, the average kinetic energy of the particles also increases. As the kinetic energy of the particles increase, they collide with the interior walls with greater force. Pressure is defined as force over area. If the pressure exerted by the gas is constant, but the total force due to the collisions increases, then the surface area over which the force is exerted must increase as well. How can the surface area increase? The only way the surface area can increase is if the volume increases as well by the piston sliding up. Okay? So, how are the volume and temperature related to each other? Well, we also learned earlier in the year that if as one variable increases, the other increases as well, they are directly proportional to each other. This relationship was first discovered way back in the late 1700s by a French scientist named Jacques Charles, who proposed Charles' law, which says the volume and temperature of a sample of gas are directly proportional to one another at constant pressure. Mathematically, that looks like volume equals a constant times temperature, where K is a constant that depends upon the pressure and the number of moles of gas. Or alternatively, we can say that the ratio of volume to temperature equals a constant. What does that look like graphically? Well, we also learned earlier in the year that if two variables are directly proportional to each other, then if we were to graph volume as a function of temperature, as temperature increases, the volume should increase in a linear fashion and go through the origin. Once again, we can consider a problem in which the conditions are changing. If we have a certain set of initial conditions, V1 is the initial volume, T1 is the initial temperature, the ratio is equal to a constant. But again, if I change either the volume or the temperature, the other one changes too, and now I have a new set of conditions, V2 and T2. Well, as long as pressure and moles are constant, K is the same for both. Once again, if they are both equal to K, these two expressions are equal to each other, and we have Charles' law for changing conditions, V1 over T1 equals V2 over T2, and once again, we are going to solve for a missing variable if we're given 3. So here's an example of such a problem. A sample of nitrogen gas at 0.0 degrees Celsius occupies a volume of 23.5 cubic centimeters. To what temperature must the sample be raised in order to increase the volume to 31.6 cubic centimeters? Well, we'll begin by writing out the equation that governs the variables. Because we see that volume and temperature are changing, we're going to write out Charles' law for changing conditions, V1 over T1 equals V2 over T2. We'll list our variables. Our initial temperature is 0.0 degrees Celsius. Our initial volume is 23.5 cubic centimeters. Our final temperature is what we're trying to find. Our final volume is equal to 31.6 cubic centimeters. So to isolate T2, the best way to algebraically rearrange this is to cross-multiply and divide. When I cross-multiply this expression, I get V1 T2 equals T1 V2. To isolate T2, I will divide both sides by V1. V1 cancels, and I get my rearranged expression, T2 equals T1 V2 over V1. Now I can go ahead and plug in. My initial temperature is 0.0 degrees Celsius. My final volume is 31.6 cubic centimeters. My initial volume is 23.5 cubic centimeters, degrees Celsius. Plug in my calculator and I get 0. Wait, what? Something's going on here. This is really strange. Because if this is correct, then that means it doesn't matter what my initial and final volume are. My final temperature is going to have to be 0. What's wrong? I'll tell you what's wrong. What's wrong is that we cannot use temperature in degrees Celsius. Degrees Celsius is not a valid temperature. What we need to use is temperature in the absolute temperature scale, which is degrees Kelvin. And we will convert from degrees Celsius to Kelvin by adding 273.15, I'll go over this in the next slide, to give us a new temperature of 273.15 Kelvin, or rounding to the correct number of significant figures, 273.2 Kelvin. So now let's go back and fix our problem. We will now plug in T1 in correct units of Kelvin, 273.2 Kelvin. Now, that was 23.5 cubic centimeters down there for my volume. Now, cubic centimeters cancel cubic centimeters, and I get my final correct temperature as 367 Kelvin as my final temperature. So let's talk for a minute about the Kelvin temperature scale to make sure we understand this. Here are some diagrams that show the relative temperature scales. On the left we have degrees Celsius, and on the right we have Kelvin. The symbol for degree Celsius is the superscript degree Celsius. The symbol for Kelvin is K. Now, let's put some values on this that we know about. We know that the melting point of pure water in degrees Celsius is 0.00, and the boiling point of water is 100.00 in degrees Celsius. Experiments that we will talk about later this unit let us determine that absolute zero the hypothetical temperature at which all molecular motion will stop is negative 273.15 degrees Celsius. Therefore, on the Kelvin scale, absolute zero is 0.00. The melting point of water would be 273.15 Kelvin, and the boiling point of water would be 373.15 Kelvin. So our equation is as follows. Temperature in Kelvin equals temperature in degrees Celsius plus 273.15. And that is a conversion that you may need, and it will be given to you. Let's continue. Finally, how are pressure and temperature related to each other? Let's do an experiment in which we take a sample of gas now in a sealed container, so the volume occupied by the gas is constant, and we have a pressure gauge on top that lets us measure the pressure. What happens to the pressure exerted by the gas as we increase the temperature at constant volume? Well, as you would predict, and it is shown on the little pressure gauge at the top, as the temperature increases, the pressure increases as well. Why would that be? How does the kinetic molecular theory of gases explain why, as the temperature increases at constant volume, the pressure increases as well? Well, let's think about it. According to the kinetic molecular theory, as the temperature of the sample of gas increases, the average kinetic energy of the particles increase. As the kinetic energy of the particles increase, they start moving faster, and therefore they collide with the interior walls of the container with greater force. Pressure is force over area. If the volume of the container is constant, then the interior surface area, or A, is constant as well. So if the force increases, the pressure must also increase. So how are pressure and temperature related? Again, if as the independent variable increases, the dependent variable increases as well, they are directly proportional to each other. This relationship was first quantified by a French scientist named Joseph Gay-Lussac, and Gay-Lussac's law says that the pressure and temperature of a sample of gas are directly proportional at constant volume. Mathematically, again, that looks like pressure equals a constant times temperature, where K is a constant that depends upon the constant volume and number of moles of gas in the sample, or the ratio of pressure to temperature equals a constant. What does that look like graphically? Well, like any direct proportionality, if as the temperature increases, the pressure increases in a direct proportion, then it looks like a straight line with a positive slope. And now we know, of course, temperature must be in Kelvin. Same deal as before. We have a certain set of initial conditions, P1 and T1. The ratio is equal to a constant. We change pressure or temperature. The other one changes too. And once again, as long as the volume and number of moles are the same, our value of K is the same. So we have, again, P1 over T1 equals P2 over T2. Given 3 of the 4 variables, solve for the 4th. I don't think we need to do an example of this because you get the idea. Now, let's put everything together. We have 3 gas laws. Boyle's law says the product of the pressure and volume equals a constant. Charles' law says the ratio of volume to temperature is a constant. And Gay-Lussac's law says the ratio of pressure to temperature is a constant. By the way, I know what you're thinking in the back of your mind, and that is Bob going to make me memorize all of these names? And the answer is no, you do not need to memorize these. You'll see why in the next video, why it's not necessary. But for now, let's think about this. Pressure and volume are always multiplied together in the numerator. Temperature is always in the denominator. So we can combine all of these to come up with a single gas law that relates pressure, volume, and temperature, and that is called the combined gas law. And the only condition for which is necessary for the combined gas law to hold is that N, the number of moles of gas particles in the sample, must be constant, or for changing conditions, P1 V1 over T1 equals P2 V2 over T2. probably the most challenging type of problem in this unit. There are 6 variables in this relationship, and you will see a problem in which you are given 5. You must rearrange and solve for the 6th. We will do an example of that in class, and I will see you then.